Hello, welcome to assembly programming on the Intel 8085. So this is the first video in a series that I will make about assembly programming for this old 8-bit microprocessor. Here you can see a picture of that physical processor. It's a 40-pin dual inline package high performance metal oxide semiconductor integrated circuit. But in this series of videos, we're mainly going to be focusing on the actual programming side instead of the interfacing, because there are a bunch of different resources for that. But I think for the assembly programming, I did not find that many solid, usable resources that are really good for learning assembly programming. So before we get to programming, we have to discuss the structure, the architecture of the microprocessor, and addressing. So on the right here you can see a sort of a block diagram of the Intel 8085. This is not of course this is not the internal circuitry, but this is sort of a higher level diagram that really emphasizes the different functions of the circuits inside the processor. So of course we have a register file here with 6 general purpose registers, which can be grouped into 3 register pairs, BC, DE, and HL. We have a 16-bit stack pointer and a 16-bit program counter as well. So the function of the program counter is it always points to the next address in memory where it's going to fetch an instruction. So the microprocessor works by communicating with memory and I/O, and of course the instructions, or for the most part, the instructions that are transmitted to the microprocessor come from memory. So the program counter basically points to a location in memory where the next instruction will be fetched. The general purpose register files are basically for the programmer's use to perform whatever computation or function that he or she would like. Of course, they're 8 bits, so maybe not as versatile as modern day 32 or 64-bit machines, but still can be used to do quite a few things. The accumulator is a special register. It lies outside of the register file, and the reason for that is because it's involved in nearly all arithmetic computations. The reason I say nearly all is because there are a couple, for example, double register add, which we'll talk about later in another video, that involves 16-bit addition using H and L and not the accumulator. There's a temporary register here which can take on a value from any register in the register, or any general purpose register in the register file. The flag register is important because it signals the result or condition of the processor after some instruction, and the result can be used to determine whether a jump should be taken, or a branch, or any other program control flow that is conditional uses that. It's also used as a way to send information, for example 1-bit information. If there's an error, for example, you can set the carry flag, and another routine would read that and understand that that is an error. So addressing is a major part as well. Addressing is basically refers to how you're getting data to the microprocessor. The first one is register addressing, and this is the simplest. It is basically registers or register pairs used as instruction operands. So basically, if you wanted to move, for example, the value in C into B, then what you would write is move B comma C, because the target goes first and then the the source, and that would be register addressing. The second one is immediate addressing. It's basically using literal data that is stored in memory as an operand. If we wanted to initialize some values, for example, load the stack pointer, LXI, SP, and then a 16-bit immediate data. Most of the time when we are assembly programming, immediate data will be expressed in hexadecimal, and so 16 bits will require 4 hexadecimal digits, and 8 bits will require 2 hexadecimal digits. The third addressing mode is direct addressing, and that's when memory address is used as a literal. What I mean by that is, for example, if you wanted to jump to another section of a program, you would have to explicitly insert the memory address of the new section of the program, and that would be direct addressing. And we'll talk about that more as we get started in assembly programming. And finally, indirect addressing is when we have the memory address referenced by a register pair. And of course, we'll see more of that as well. So most resources, when you're learning assembly programming, they'll save the stack for later on. But this is a fundamental computation structure, and we need it for the first class of instructions that we are going to be studying. And this is the stack. So the stack is a structure which grows on the 8085 at least, or on all Intel processors. It grows towards lower addresses from the top down. So this is why I have a stack of plates facing downwards. The way the stack works is whatever is first in gets pushed out last. So this plate that's at the very top will get used last, if that makes sense, if you have the gravity going towards the top. The stack is addressed by the stack pointer. So the stack pointer is the register that you'll use to reference a particular item in a stack. And stack pointer is usually initialized to be the highest available memory address, and it just grows down from there. So that brings us to the instruction set. The 8085 has a total of 80 instructions, which is actually 2 more than the 8080. But essentially, the instruction set encompasses an alphabet. It represents everything that the microprocessor is able to understand and able to execute. If you can't do it with instructions, you cannot do it at all. So no matter how good you are at assembly programming, if what you're trying to do cannot be done with the instructions in the instruction set, then it is impossible to accomplish. Okay, so that brings us to an exciting part. The first section of the instruction set that we're going to be talking about. These are the data movement instructions, and this is good because we have just talked about addressing, and I want to apply that here. For each class of instructions, I'm going to divide them up into 2 different groups, one for 8-bit and another for 16-bit instructions. So let's start with the 8-bit. The simplest data movement instruction is MOV, and it uses register addressing. It uses 2 registers as operands. So if I wanted to move the value of the register D into B, I would just say MOV and then space B comma D, because D is the source and register B is the target or destination. MVI uses both register and immediate addressing. Remember, we have to specify a register that we want to move the immediate data into, and then we have to specify a 2 hexadecimal digit immediate value. So I could do MVI A, comma 39H, and the H means hex. One thing that you have to memorize or remember when using MVI or any immediate addressing instruction is that if your immediate data begins with a letter, for example, A, B, C, D, E, or F in hexadecimal, you have to put a 0 in front of it to tell the assembler that what you have here is indeed a number. If you're writing in decimal, of course, you're not going to have any letters, and binary doesn't either. And we'll talk about that a little bit more as we write some sample programs. Another instruction is LDAX, and this one uses indirect addressing. The operand here is either going to be B, D, or H, because the X means or symbolizes register pair, and what this instruction does is it loads the accumulator, that's what LD stands for, loads the accumulator with the value in memory referenced by the register pair that you specify as the operand. So LDAX B would put whatever value is in memory location specified by BC into the accumulator. LDA uses direct addressing in that the data that we specify here is going to be kind of like an immediate data. It's going to be 16 bits or 4 hexadecimal digits, and it's basically going to load exactly that value into the accumulator. So LDA 1000H would load the memory contents of 1000 into the accumulator. STX and STA, basically the same thing as LDX and LDA, except it stores the accumulator into memory instead of the other way around. One thing that I want to discuss about the memory here is that IM is basically a reference for H and L, the memory location specified by H and L. So if you wanted to move the value of whatever reference by H and L into the accumulator, you would just say MOV. You would use MOV, not these. MOV A, comma, M. And now move that into the accumulator. In and out communicate with input-output devices. For now, that won't be that important, but later on, as we create some basic interfacing programs, then these will be necessary. These do not take operands. Actually, they take one direct operand, which specifies the address of the port, and the accumulator goes out to that port. Okay, so 16-bit data movement. LXI will basically load a register pair with a value. LXI can be applied to B, which represents BC, D, which represents DE, H, of course, and the stack pointer. LHLD and SHLD store the value of H and L into a specified memory location, kind of like LDA and STA, but it's 16 bits. XCHG is nice because you can exchange, that's what it stands for, exchange the value of D and E with H and L. Notice that if you wanted to exchange B and C with D and E, you have to manually move the 8 bits, so you would have to move B into D and then move C into E. So that's kind of a pain. SPHL is basically going to put H and L into the stack pointer. XTHL is exchange the top of the stack. Remember, that's what the stack pointer points to with H and L. And then push and pop are going to be the main instructions involving the stack, in which we add or remove items from the stack and change the stack pointer accordingly. So now with that, we're going to do some sample programs to demonstrate some of these data movement instructions. So all of these can be written just with the data movement instructions. We're going to write optimal assembly routines, which end with halt instructions that do the following 3 items. What I mean by optimal is that it takes up minimal memory and it takes a small amount of time to execute. Okay, so let's go ahead and try the first one out. So the first one says store the contents of register B into memory location 1200 and saves the accumulator in register B. So before we do any of these, I'm going to do like initialization, init here, and the reason I'm going to do this is because we have to see that it works. And we can't do that when everything is initialized with FF. We can't see if things got moved around. So I'm going to begin by initializing the accumulator with the value 39 hex. So these are just random values. It just really doesn't matter what I put here. And I'm going to move into B 64H hex. Okay, and now I'm going to start writing my program. So I'm going to start with the start label. And what I want to do first, remember, is store B into memory location 1200. So the way I can do this is, well, there's a couple of ways. I can either use the STA thing by moving it into A, or I can load it into an address referenced by another register pair. For example, HL. So I would LXI H, you don't need the L, and then my immediate data will be 1200 hex. Okay, so now M, remember M now holds the value that we want to, or we want B to go into. So the way we do that, MOV into M, or B into M. So remember, this is the destination and this is the source. What we want to do now is move the contents of A into B. So we do that by doing MOV B, comma A. Again, source and destination. After that, we are done and we don't need to do anything more, so we halt the program. Alright, so now I'm going to assemble and load here so that you can see it in the memory. And I want you to notice something is that the initialization took up 4 bytes, so our program in actuality is only 6 bytes in size. That is a very, very small program. Of course, it doesn't do that much, but it's a very small program. What we want to do now is look at 1200, the memory location 1200, and see if the initialization of B goes there. So I'm going to step through this program, MVI A 39, and there. So now we have everything initialized. So the first thing you'll see is 1200 pop up at H and L. We're going to move B into the address of H and L. So you can see 64 got there, and now we're going to move A into B and halt. So in the end, you can see the program did its job. And with initialization, it took 40 T states, which is very, very tiny, and everything worked here. What I want to do now is show you something, is show you another way to do this problem, but it's going to be less efficient. Okay? What I'm going to do now is, remember, 40 and 6 bytes, because you're going to compare it with this other way. What we're going to do now is move A into some other register, for example C, that we're not using, and then move B into A. Then we're going to do the LDA thing, and then after that we're going to move the value of B, or value of A into B, which now is in C, so move C into B, and then halt. So I'm going to again assemble and load. And I don't know if you can see from the tab there, but it was 11 bytes. Initialization was 4 bytes, so the program is 1 byte more than the original. So it's already looking not so good, but still okay. And let's go ahead and run it. So initialization complete now. And we're going to move A into C, save it there, move B into A, load. Oops. Okay, so that is where I have a problem. If you see, what happened was I put LDA, but we're actually storing it, so it's STA. Okay, so it's 11 bytes still, and let's go ahead and run it again. Initialization complete, move C into A, move A to B, there we go, we have that there, and halt. Now you can see it took 4 more t states, so the first way is a little better. Again, in large programs this will not be a big issue, but I just wanted to show you there's always an optimal way to do things. Alright, so that's number 1. Number 2, we're going to swap the current top of stack with the BC register pair. Remember, we have a way to do that with H and L, so we can go ahead and take advantage of that here. And I'm going to rewrite the initialization. So the current top of stack, I'm going to go ahead and put something on the stack here. So let's put 1, 2, 3, 4 hex, and then we're going to push that onto the stack. Oops, push B. And then we're going to load B with something else, 5, 6, 7, 8 hex. Now our job is to replace this with the top, or swap with the top of the stack. The best way to do this, I think, would be to first move BC into H and L, and then do exchange top of stack with H and L, then move back. So to do that, I would do move from C to L, then move B to H, exchange top of stack with H and L, and just move everything back. You can see there's kind of a symmetry here, and we'll see if this program works. So, assemble and load. There was 13 bytes loaded, and if we take a close look here, 1, 2, 3, 4, 5, 6. So our program is actually only 6 bytes, and our stack is going to be way down here, so we're going to have to keep an eye on this. Okay, so now everything is properly initialized. We have 1, 2, 3, 4 on the stack, 5, 6, 7, 8 in B. Let's go ahead and run it. Alright, so now we have 5, 6, 7, 8 in the stack, and then 1, 2, 3, 4. One thing I wanted to mention was, you see it kind of looks backwards on here, but the reason for that is because the Intel 8085, like most other 8-bit processors, is Little Endian, which means the least significant byte is stored in lower memory address, which makes sense in a way. So we have 69 T states, which is a little longer than last time if you recall, but the program worked and it was only 6 bytes. So we have accomplished 2. Now let's look at 3. Moves register pair BC to DE, DE to HL, and HL to BC. Wow. So again, there's a couple of ways to do that, and I'm going to initialize some values here. Okay, so now we should see this value getting pushed into D, this one going to H, and this one going to B. Okay, so how do we do this? It's not very hard. So I'm going to do one way first and then show you the better way to do it. The first way to do it, obviously, is to push everything onto the stack and then pop them in the order that you want. So we want, remember, we want value of H to go into B, so that happens here. We want the value of H to the value of D to go into H, and then of course D to go from B. So the thing with push and pop is that there's nothing saying that you have to push registers in the same order that you pop them. So we can push H and then pop B, that's perfectly fine. It's just that whatever was in H will go into B instead of into H. So let's go ahead and assemble and load. So you can see there's 16 bytes with initialization. That would be 1, 2, 3, 4, 5, 6, 7. So only 7 bytes. Now let's go down, way down to the stack. Remember, stack pointer is at the bottom. And let's go ahead and run this thing. So everything is initialized now. We should see B on the stack, D on the stack, H on the stack. Then we're going to pop B, pop H, and then halt. So you can see everything worked as normal. 101 T states. I think we can do better. So here's what I'm going to do. Remember how there's an instruction for exchange DE with H and L? Well, one of those directions, DE to HL, is what we want. The other one, HL to DE, is not exactly what we want, but we can fix that very easily. So to show you what I mean, I'm going to go ahead and do this. So I'm first going to save the value of B. It doesn't really matter which order you do this, but then I'm going to exchange. And then, after I exchange D and HL, I'm going to move into B, or sorry, I'll do the lower order first. I'll move basically DE into BC. After that, I'm just going to pop into D. So you can see the program already looks shorter. 15 bytes loaded, so you can see it's 1 byte shorter. And let's go ahead and run this thing. So now initialization is complete. We're going to push B onto the stack, exchange those, then move that there, pop D, and then halt. So you can see this one took only 69 T states compared to 101. So this program is more efficient, and I believe it might be the optimal one. So now we've completed all of the problems here. You'll see some additional problems that you can solve in the comments section and comment on each other's codes. And so I hope you enjoyed this video. I hope you learned something, especially something that you didn't know before from, for example, high-level programming languages. And I'll see you in the next video. Make sure to like and subscribe, and take care.